This lesson is section 11.3 on combinations. Items that are selected from the same group that are not used more than once, so no repeats, but in which the order of the items makes no difference, are when you'll use combinations. Okay, so remember, there can be no repeats and the order does not make a difference. Okay, situations like committees, delegations, identical prizes, identical jobs, those are the kinds of scenarios you'll come across that use combinations. Now, when we talked about permutations before, we found that anytime we use a permutation, we also could do the same problem using the fundamental counting principle. With combinations, though, the only formula that's going to work is the combination formula. So you have no other options when it's a combination but to use a combination. Now, the notation for a combination is very similar to that of a permutation, but we're going to have a C instead of a P. So NCR is what indicates a combination. The N is still the total we're selecting from. And the R is still the number being selected. Now, just like with a permutation, there is a fancy formula for a combination. It's equal to n factorial over the quantity n minus r factorial times r factorial. This formula will be on your formula sheet. Whether or not you want to use it, I personally say go with your calculator. You can access the combination button on your calculator just like you did the permutation button. You're going to go to that PRB probability button, and the second option over will say NCR. All right, let's look at an example. In the previous lotto system in Florida, you had to pick 6 numbers, 1 through 49. The order in which you selected the 6 did not matter. You just had to match those 6, but order did not matter. We want to know how many 6-number picks were possible. So, because we're not going to have any repeats and the order does not matter, we can use a combination. Okay? So, we would have 49 numbers being considered, but we're going to choose 6 of those numbers. Okay? Now, if you use your formula, it would be 49 factorial over 49 minus 6 factorial times 6 factorial. Okay? You're also welcome to put that into your calculator, which is what I would encourage you to do, and you're going to find that you get 13,983,816 possible ways. Now, today in Florida, when you play the Florida Lotto, you still pick 6 numbers, but now it's from 1 to 53. So we want to figure out how many 6-number picks are possible in that situation. So we have 53 numbers we can choose from, and we're still going to choose 6. Okay? Plug this into your calculator, and you're going to find that we get 22,957,480. So it's a little more difficult to win the Florida Lotto these days than it was in the past. A congressional committee consists of 4 senators and 6 representatives. A delegation of 5 members is to be chosen. So remember, on that first slide, I told you that if you ever come across a delegation, that's one of those situations where you're going to want to use a combination. So the first question asks us how many delegations can be formed. So if we have 6 senators or 4 senators and 6 representatives, that means that we have a total of 10 that we're choosing from. Okay. And of those 10, we're trying to come up with a delegation of 5 members. Okay. So 10 choose 5 would give us 252. The next question asks us how many delegations can be formed if each delegation must include 3 senators and 2 representatives. So we've got to consider 2 things going on here. First, we've got to consider our senator slot, and then we've got to consider our representative slot. Now remember that those 2 slots will be connected by multiplication. Okay? Now when I consider my senators, there are 4 senators that I can choose from, but I'm going to only pick 3 of them. And with my representatives, there are 6 representatives I can choose from, but I'm only going to pick 2 of them. So I'm going to have 4C3 times 6C2. And when you do that in your calculator, you're going to find out that the first one is equal to 4, the second one is equal to 15, and 4 times 15 gives us 60. Okay. The last question on this slide asks us how many 5-member delegations can be formed of senators only. So think about this one. There's only 4 senators, and if we want to construct a 5-member delegation, can we do it? Nope, we can't. Since there's only 4 senators, you cannot select 5. So how many 5-member delegations can be formed? 0. The next example asks us about committees. Committees is another one of those items that I mentioned in the beginning that will use a combination. This says how many 3-member committees consisting of all women can be formed from a group of 4 men and 5 women. So when we consider the fact that initially we're only looking at women, we want a committee of all women, and there are 5 women, we need to do 5 choose 3. So there's 5 women being considered, and of those 5, we're picking 3 for a 3-member committee. We don't even care about the men in this case because this first committee asks us about all women. And we'll find that 5 choose 3 equals 10. There are 14 standbys who hope to get seats on a flight, but only 6 seats are available on the plane. How many different ways can the 6 people be selected? Okay. So there are 14 people on standby, but of those 14, only 6 are going to get seats. That tells us that there are 3,003 different ways that those 6 people can be selected. Of the 100 people in the U.S. Senate, 18 serve on the Foreign Relations Committee. How many ways are there to select Senate members for this committee, assuming party affiliation is not a factor in the selection? Okay. So if there are 100 people in the Senate, and of those 100, we want to choose 18, we would find out, this one's a big one, that there are 3.06645,108 times 10 to the 19th different ways that these Senate members can be selected for the committee. Okay. That number was so large that I went ahead and wrote it in scientific notation. 50 people purchase raffle tickets. 3 winning tickets are selected at random. If each prize is $500, in how many different ways can the prizes be awarded? Okay. Prizes are another thing that I mentioned in the beginning as being combination. Since we have prizes here, we know we're going to use a combination. Okay. Now, there are 50 people that purchase raffle tickets. And of those 50, we're only choosing 3 people to win the prize. So we would have 50 choose 3, and that's going to equal 19,600. Now, this next example we have to be careful on. It says an employment agency has listed 5 highly skilled workers. In how many ways can 2 of these workers be selected if A, the first one selected is to be the foreman and the second one selected is to be the assistant? And then part B asks us the 2 selected are both sent to do the same job. Now, in part A, we have to be careful because it says the first one selected is to be the foreman. It says the second one to be selected is to be the assistant. So in this case, order matters. When order matters, remember, that's not a combination, that's a permutation. So in this case, of the 5 people being considered, when we choose 2, we have to make sure that we use a permutation here, not a combination, because order matters. And that would give us 20. Now in part B, it says that the 2 are selected to do the same job. Now I mentioned on the very first slide that with delegations, committees, and identical prizes, identical jobs is another one that uses combinations. So part B will be a combination. Order does not matter in this case because they're doing the same job. So here we would have 5C2, and that's only going to give us 10 options. So you need to be really careful as you go through these problems and ask yourself, does order matter or does it not matter? If order is important, you have to remember you can use a permutation. If order does not matter, that's when we use our combination. So sometimes the tricky part can start to become, well, which one do I use when? So you've got to make sure you're asking yourself if order matters or not. Sometimes you're going to find that you end up using the fundamental counting principle in combination with a permutation, or the fundamental counting principle in combination with a combination. So, in this next one, it says that Brett went to the party store to buy 3 types of party favors and 6 kinds of game prizes. There are 8 types of party favors available and 10 kinds of game prizes. And how many ways can he make his selection? So, when we look at this, the very first slot we're going to have is going to be favors, and we're going to multiply that by another slot of game prizes. Okay. Now, within the favor slot, we have 8 to choose from, but we're only going to pick 3. Within the game prizes slot, we have 10 to choose from, but we're only going to pick 6. Okay. Now, we saw an example similar to this when I looked at senators and representatives a few problems back. I just didn't mention it to you at that point. But we have a fundamental counting principle going on with a combination because we've got 2 slots we have to fill out, but within those 2 slots we're filling them out with combinations. And remember that we always need to multiply. So we're going to find that this is 56 times 210, and that's equal to 11,760. The next example says from 12 dogs, 6 will be chosen to be taken to a nursing home for the clients. In how many ways can the 6 dogs be chosen? Okay, so order is not important here. We're not picking them in a certain way. We're just saying 6 of them are going to go to the nursing home. They're all doing that same activity. So we have 12 dogs that we're going to choose from, but we're only going to pick 6 of them. And that would give me 924 combinations. Let's look at another dog selection problem that is going to give us a little bit of a different scenario. This says that from 12 dogs, 4 will be chosen for each of these activities. 1 will be neutered, 1 will get a bath, 1 will get a distemper shot, and the other will get clipped. In how many ways can the 4 dogs be selected? So in the previous dog problem where we talked about bringing 6 of them to the nursing home, all 6 of those dogs were doing the same activity. They were all going to the nursing home. In this case, the 4 dogs that are being chosen are doing different activities. So since they're doing different activities, we have to use a permutation. Okay, so this would be 12p4, and that's going to give us 11,880. Okay. So the challenge really starts to become, do I use a permutation? Do I use a combination? Do I use fundamental counting principle? Sometimes you're going to have to use them in combination with each other. So you really have to start paying attention to whether or not order matters, if there's any repeats. Okay. In the remaining examples I'm going to go through with you, we're going to start to make those decisions. Are we going to use a permutation? Are we going to use a combination? Are we going to use fundamental counting principle? Are we going to use some combination of those? Okay. The first example we're going to look at says 4 identical prizes are being given to 4 lucky people. As soon as I see that identical prizes, I should realize that I'm going to use a combination. These 4 winners will be chosen from 12 contestants. How many ways can the prizes be awarded? So, since it's identical prizes, we know we're going to use a combination. We have 12 contestants, but we're only going to choose 4. And that will give us 495. The second example says license plates are made using 3 letters followed by 3 digits. How many plates can be made if repetition of letters and digits is allowed? So, because repetition is allowed here, we're going to make sure that we use the fundamental counting principle. Okay. So, when I look at a license plate in this scenario, I'm going to have 3 letters, and then it's going to be followed by 3 digits. Okay. Remember that there's 26 letters in the alphabet. So in my first 3 letter slots, I'm going to have 26 options in each of those slots. Okay. The last 3 slots are digits. Remember that 0 through 9 is 10 different digits. So in each of my digit slots, I'm going to have 10 options. And remember that we always connect these with multiplication. So we're going to have 26 times 26 times 26 times 10 times 10 times 10. When we multiply that out, we're going to find that 17,576,000. Number 3 says, from the class of 15 students, a president, vice president, and treasurer are to be selected or elected. How many different slates of officers are possible if no one may hold more than one office? So, anytime you're looking at officers of a club, order is important. Since order is important, that means we're going to use a permutation. Okay. So, we have 15 students that we're choosing from, but we're only going to choose 3 of those because we have a president, a vice president, and a treasurer. That's 3 slots that need to be elected. Okay. 15P3 would give us 2,730 ways to slate those officers. Number 4 says a delegation of 5 students must be chosen from a college to attend a convention. As soon as I see that word delegation, it's screaming combination to me. How many different delegations can be chosen if there are 10 eligible students? So we're going to have 10 students. We are choosing only 5 of them though. So we're going to have a combination, and it's going to equal 252 different ways that we can choose those 10 eligible students. Number 5 says 7 runners compete in a race for which there will be first and second prizes. In how many ways can the prizes be won? Okay. Now, order is important here because we're looking at a first and second prize. So, technically on this one, you could use the fundamental counting principle or you could use a permutation. I personally would just use a permutation. We have 7 runners that we are choosing from that are competing in the race. And of those 7, we're going to give prizes to 2 because we have first place and second place. And that would give us 42 different ways that the prizes can be won. Number 6 says that license plates are made using 4 digits followed by 2 letters. How many plates can be made if repetition of both letters and digits is allowed? So, because repetition is allowed, we know that we're going to use fundamental counting principle. Okay. So, I have the first 4 slots, which have to be digits, and remember there's 10 digits in 0 through 9, and that the last 2 slots are going to be letters. Okay. There is a restriction here though. It tells me the first digit cannot be 0. So since the very first digit cannot be 0, we're talking 1 through 9, and in that case there are only 9 digits that we can put in the first slot. In the remaining 3 slots that call for digits, there's going to be 10 options because we can use 0 through 9. And then there are 26 letters in the alphabet. Remember, all of these need to be connected by multiplication. When we multiply that out, it gives us 6,084,000. This next example, number 7, says, if you flip a coin 5 times, how many total outcomes are there? Okay. So when we flip a coin, remember that it can either land on heads or it can land on tails. Okay. So if we flip this coin 5 times, we're going to have 5 different slots we can look at. Okay. And each of those times we have 2 options because it could be head or tails. So we're going to want to use the fundamental counting principle in this case. And remember that all these 2's are going to be connected by multiplication. Okay. You can multiply out these 2's. Also remember that this is the same as 2 to the 5th. And we're going to find out that there are a total of 32 outcomes if you flip that coin 5 times. Number 8 says a city soccer league has 7 teams. In how many possible ways could the league assign the first and second place trophies at the end of the season? So because I see that they're going to be first and second place trophies, I know that order is important. Remember, when order is important, I have to use a permutation. So I have 7 teams, and I'm going to pick 2 of them. And because order was important, remember I used a permutation. This tells me that there are 42 different ways those trophies could be handed out. Number 9 says that the math club at TCC is made up of 53 people, 22 males and 31 females. Suppose the club... Alright, I had a reminder come up on my iPad, which is how I'm recording this, that my best friend's getting married today. So I think it paused our recording, so if I am going back and repeating a problem or two, I apologize. Okay. Number 7 says if you flip a coin 5 times, how many total outcomes are there? Okay. So when we flip a coin, remember that it's going to either land on heads or it's going to land on tails. So each of those 5 times we flip the coin, we have 2 different options that we're considering. It could be heads or it could be tails. Okay. So we're going to use the fundamental counting principle, and remember that each of these 2's needs to be multiplied together. We can multiply out those 2's, or we can also just put in 2 to the 5th in our calculator, and that's going to tell us that there are 32 different outcomes in terms of how we could flip that coin. Okay. Number 8 says a city soccer league has 7 teams, and how many possible ways could the league assign the first and second place trophies at the end of the season? So, key here is that there are first and second places, so that means order is important. When order is important, use a permutation. Okay. So we have 7 teams that are in the league, and we're only going to pick 2 of those teams, one for first and one for second. That's going to tell us that there are 42 different ways we could hand out those first and second place trophies. Number 9 says the math club at TCC is made up of 53 people, 22 males and 31 females. Suppose the club elects officers for president, vice president, secretary, and treasurer. Find the number of ways to select the officers if each must be a male. So, because each of these officers must be a male, there's actually some extra information in here. I really don't care that there are 53 people in the club, and I really don't care that there are 31 females. What's important to me here is that there are 22 males because all of my officers must be male. Now, remember too that when we're electing officers, such as president, vice president, secretary, and treasurer, the order matters. And since order matters, we're going to use a permutation. So, because we're only considering males, we're just considering 22, and we're going to pick from those 22, 4 of them. So that tells us that there's 175,560 different ways that we can elect those 4 officers as long as they're males. Example 10 says that Amanda is giving a bridal shower for her friend's daughter. Due to her hectic schedule, she decides to hire a caterer. The caterer offers 15 appetizers and 12 desserts. Amanda decides to choose 5 appetizers and 4 desserts. How many ways can her selections be made? Okay, so this is one of those problems where we're going to have the fundamental counting principle and combinations combined. Okay, order does not matter here. It doesn't matter what order she picks her appetizers and her desserts. Okay, so because order does not matter, we're going to use a combination. When we select the appetizers, there are 15 she can choose from, but she's only going to pick 5. When we pick the desserts, there are 12 desserts she can choose from, but she's only going to select 4 of them. Okay? And remember that these two numbers need to be multiplied. So we have 3,003 ways to pick the appetizers and 495 ways to pick the desserts. When we multiply those two numbers together, we find out that there is 1,486,485 different ways she could pick a combination of appetizers and desserts. Number 11 says 6 high school seniors are to be selected from a group of 30 high school seniors. Each of the 6 will receive a free ticket to grad night at Walt Disney World. How many ways can the selection be made? Okay, so this one's kind of like a prize. If you're getting a free ticket, sort of like you're getting a prize. So these seniors are getting the same prize. And remember that I mentioned when we're getting the same prize, we use a combination. So there are 30 high school seniors, and of those 30, 6 of them are going to get this prize of a free ticket to grad night. So we have 30 choose 6, and that gives us 593,775. All right, we're almost there. This is the last slide. This says that number 12 is 10 people volunteer to work in a brain bowl competition. Only 4 are needed to work, though. 1 would act as moderator, 1 would keep score, 1 would keep time, and 1 would be a runner. Assuming all 10 people could perform all the tasks, how many ways could the assignments be made? Okay. So in this case, it's kind of like electing president, vice president, secretary, or treasurer. The order matters. So since order matters here, we are going to use a permutation. Instead of president, vice president, secretary, and treasurer, in this case we have moderator, scorekeeper, timekeeper, and runner. Okay. So there's 10 people we're going to choose from, and of those 10, we only need 4. So that's going to give us 5,040. Okay. There is no 13. I don't know where it went. I probably just misnumbered problems. Okay. But the last problem is number 14. Okay. Maybe I was just trying to avoid that unlucky number 13. It says, in how many ways can 7 children line up for lunch? Okay. So when the children line up for lunch, order All right, sorry, I got a phone call, so we had a quick interruption there. When the 7 children line up for lunch, okay, in that first slot we could have 7, in the next slot we could have 6, then 5, then 4, then 3, then 2, then 1, okay? So if we look at this, this is using the fundamental counting principle. And since we're multiplying these numbers all the way down from 7 to 1, we can enter this into our calculator as 7 factorial, and we'll find out that it's 5,040. Okay. This one actually can be done with a permutation as well, and you can do 7p7, and you will get the same result. Okay, so when you're lining up, whether it's children in line, any kind of line, the order is going to matter. So you can use permutation or you can use fundamental counting principle. I don't know about you guys, but I either wanted to be the caboose or the line leader. Okay, I didn't want to be one of those people in between. This is the last example we have from 11.3. So realize that at this point, you have permutations, you have combinations, and you have the fundamental counting principle. And you need to be at a point where you can decide which one to use when. Okay. Remember that if the order does not matter, and we're looking at things like combinations or committees, delegations, identical prizes, and identical jobs, you're going to use a combination. If the order does make a difference, you're going to use a permutation, okay? The situations in which you use permutations, you can typically use fundamental counting principle as well, but usually using a permutation is just going to be faster for you. But situations in which repetitions are allowed tends to be the types in which I will use a fundamental counting principle over permutation. Okay, so if repetitions are allowed, we're going to use fundamental counting principle. If there's no repeats and the order does matter, that's when we use permutation. And when there are no repeats and the order doesn't make a difference, that's where we're going to use a combination. Okay. Now, make sure that you go through all of these examples, you understand them. If you have questions, please make sure that if you have any questions on any of these examples, make sure that you find me before our next class to get any questions you have answered. We're going to move forward on Friday with 11.4.